Very much, Caleb. The talk I'm giving today is based on a lot of the dissertation research I did while at Rutgers and some work after that. This is my disclaimer. None of this work was done while I was at Equinor or at any other employed university while I was at BHP Billiton. This was all done either during my time at Rutgers or after in my free time. So I don't have to worry about any copyright issues or anything. And so, as Caleb said, today I'm going to talk about the structural inheritance in rift basins, understanding complex fault geometries and interactions, physical modeling. And the picture you see on the left here, this is the cover of the AAPG bulletin in which our most recent paper on this particular topic appeared, which was November 2017. And this really highlights the complexity of the fault patterns and interactions we were looking at and trying to understand some of the ways these form. So the outline of my talk today will be, first we're going to start with an introduction and objectives. Then I'm going to talk about the physical modeling setup. Then we're going to go into the series of models that were conducted. So the first series varied the angle between the extensional phases. And then the second series varied the magnitude of extension during the first extensional phase. And after that, I want to talk briefly about some of the quote unquote new analogs that came out after that series 2 paper was published. So at this point, they're not new because they came out in about 2013 through 2015. But at the time, they were very helpful for giving us more analogs to look at and compare the physical models to, and give us more ideas for how to analyze, especially the layered model that I made. And so then I'll talk about some of that with the 3-dimensional fault geometries and interactions. And then I want to finish up by just hitting on some of the other modeling work at Rutgers that has been done since I left. So this talk is really designed to kind of be a compilation of a few different papers and hitting the highlights of each. So the main references for the talk and the papers are listed then on this outline. And so, as I said, this really started during my dissertation work, which that was a long time ago in a galaxy far, far away. More specifically, we're looking at approximately 2007 to 2009 was when most of the initial modeling work was done. And that was done at Rutgers in New Brunswick, New Jersey. So in case you were wondering, that is where New Brunswick is located, not too far outside of New York City. And during this time, I spent a lot of time in the modeling lab, and I also spent a lot of time looking at Martha Withjack and thinking and talking about very complex fault patterns. And I have to say that this is one of my favorite pictures from that time, because it really highlights Martha and I standing around, kind of staring at each other, trying to think things through, with Roy taking pictures on the side and offering commentary when necessary. So one of the things we talked a lot about is that there are many basins that have undergone multiple phases of extension with differing extension directions through time. This initial work was really sparked by a project that Rutgers had with Husky Energy at the time. And so this picture on the right here is a picture from the Jeanne d'Arc Basin, so showing some very complex fault patterns. But we know that these fault patterns like this exist in basins worldwide. And from various seismic studies and other investigations, we know these fault patterns are very complex. They have multiple fault trends, they have multiple fault interactions, they can change with depth, and they can change on also at the scale of observation. And the problem with just having the seismic data and the natural examples, so you can only observe the final fault patterns in nature. Whereas using the physical modeling, this allows for observations of fault patterns and fault growth over time. So it's much easier to observe faults initiating and propagating and faults interacting than using the models. And so in this setup, this is actually our modeling setup. I will go into it a little more in detail in a minute, but I just want to highlight that. So we would have the model set up down here on the table, and we would have a camera above capturing deformation at certain displacement increments. And that's how we could trace how the fault patterns develop over time. So given these motivators here, really the objectives of my research was, in what ways do the pre-existing normal faults influence the initiation, propagation, and geometry of newly formed faults? And this is a case where this has been talked about. We know that there's an influence of pre-existing normal faults, but I really wanted to get at some of the more specifics and how different variations in the pre-existing fault fabric had an influence. And so this is why I focused on how does the orientation of the pre-existing normal faults affect new fault development? How does the degree of development of the first phase fault population, so the number, length, and displacement of the first phase normal faults, and then also what is the three-dimensional variability in these fault patterns. Part of the reason I agreed to do this talk, even though this research was a while ago, is these are all very fundamental questions that are applicable to multiple fields of study. So in the oil and gas industry, obviously this has an impact looking if you're looking at compartmentalization, if you're looking at fracture networks associated with faults and other deformation associated with faults, or even thinking about, as we look to the future, thinking about carbon sequestration and what potential seals versus pathways are there for injecting CO2. And so this is really why I thought, even though the work was done a while ago, this was really timely to then have this as a talk being given at the end of 2021. So as I alluded to, we addressed these questions using physical models. And one of the advantages of physical modeling, as I said, is that we can take pictures of the evolution through time, so we can actually watch the fault patterns develop. But then also we know exactly what the boundary conditions are. So I can, for example, know that how much the magnitude of extension during both phases, the angle between the extensional phases, and use that then to make inferences about the fault patterns. So the model setup, here I have a picture. So on the left, this is the map view of the rig you saw in the photo before. And then on the right, I have a cross section. And these are at two different scales, because if I had the cross section at the same scale as the map view, you would not be able to see it. So for the model setup, I started with base of the model having a mobile rigid sheet, and the motor then would be attached to this mobile rigid sheet side, and then a fixed rigid sheet. And between them was an 8-centimeter rubber sheet, which this was then defines the zone of deformation during the model. On top of that rubber sheet, then I put a 0.5 centimeter thick layer of silicone polymer. And I did this not because I was trying to model an actual ductile unit, but this was done to help decouple the clay layer from the rubber sheet, which allows the base layer of the lay to move vertically during deformation. So in models where there is not a silicone layer, you're forcing the fault displacements to zero, and I wanted to avoid that in this case. So then on top of that base, I put on a layer of wet clay, and this was 4 centimeters thick over most of the model. Over where the silicone polymer was located, it was 3.5 centimeters thick. And many of you, I'm sure, are familiar with the sandbox models and may be wondering why clay. Well, we use clay at Rutgers. We do use sand as well, but we use a lot of clay at Rutgers because the clay really allows for observation of more detailed fault geometries. So in clay, fault propagation and linkage develop more gradually than in the sand models. And this then leads to the development of more fault propagation folds, more relay ramps, and more sinuous fault traces in clay models and sand models. And so especially since I was looking to understand fault interactions and how faults initiated and propagated, this was the ideal medium by which to use in the models. So this was the base setup for all of the modeling work that was done. It was a 4 centimeter clay cake with silicone polymer in the middle. And for the different series of models, we started with a base case and then kind of varied one property from that base case. So hopefully this box here should look like the same box we were just looking at on the previous slide. And the base case model was that there was a first phase of extension that extended up in kind of this northwest direction here for a certain magnitude. And then there was a second phase of extension that extended up kind of in this northeastern direction for a certain magnitude. In the base case model, the angle between the first phase and second phase extension directions was 45 degrees. And we extended both phases for a displacement of 3.5 centimeters at about a 4 centimeter an hour displacement rate. So many of you may now be thinking, wait, you used clay, which is seems like a very sticky fluid material, and how did you make faults out of that? Well, because of scaling laws and properties of the clay, it turns out if you deform it at this low, relatively slow extension rate, you can develop localized faults and folds in the clay model, and the scaling properties work out so that deformation in the model is about, on the scale of a centimeter, roughly works out to about 1 kilometer in nature. There's a little bit of error bar on that, but that's kind of what we're looking at. So as I'm showing images of the models, you can think about, my centimeter scale bars, and it's approximately a kilometer. So for the series of experiments then, from this base case, there is series 1, which then varies the angle of the second phase extension. So we kept the first phase extension direction the same throughout, but then this E2 moved and had different angles. The second series of models then varied the magnitude of the first phase extension. So instead of then changing the angle, we kept the angle constant, and we changed just how much we were pulling during the first phase. And then also, as this base case, we made a layered model, which just involves adding a little bit of dye to the clay cake so we have discrete layers, so that we could analyze the cross sections of the model later, which is then kind of the third, it's not really a series, which is the third part of this talk. So there are some observations that we can make for all the models that are true, and these are going to be shown on the base case model. So now we're looking at a few photographs of the top surface of the clay model. The little sun indicates the lighting direction for the models. And so fault planes that are dipping toward the sun are going to appear light. Fault planes that are dipping away or down to the bottom right here will be dark. And so at the end of the first phase, you can see that there are normal faults that form in the zone above the silicon polymer. These normal faults strike roughly perpendicular to the extension direction, which is again indicated here by this arrow in the bottom left. Then the second photo is the end of the second phase of extension. And again, the light is in the same location. You can see most of the faults at least have some component of dip up to the top left. There are some that are closer to the bottom left, and that's why, for example, this fault plane appears dark. And one of the first observations we can make at the end of the second phase of this model is that many of these first phase faults are reactivated with oblique slip. So for example, if you just look at a fault trace around approximately in here, and you compare it to then the the second phase photo, and the size of the fault and the what we're seeing exposed on the top of the clay cake, you can see that the fault heave is definitely increased. And you can see also there are lines. They're subtle, but there are lines on the top of the clay cake. And we can also use these lines to help see the offset and the slip direction on the faults. In addition, there were some faults where we could actually see corrugations on the fault surfaces from the first phase and second phase, as you can see here in this picture on the far right. And this really do highlight the first phase with the dip slip behavior, and then reactivated second phase faults that definitely have oblique slip on them. So another observation we can make is that there are also new normal faults that form during the second phase of extension. And most of these new faults initiate at these pre-existing faults and propagate outward. And again, because we take photos throughout the second phase of extension, we could trace as these faults initiated and then propagated outward as we went after the experiment. And so just if we zoom in on this box here indicated on the second phase model photo, you can see that there are these faults that kind of initiate at the first phase fault and propagate outward and inevitably run into then another first phase fault. So now I'm going to talk about the series 1 models. And this is where we vary the angle of second phase extension. So what we have is a series of photographs, and the top row is the end of the first phase of 4 models. The bottom row is the end of the second phase of 4 models. And above each column is an indication of the model and the angle between the first phase and second phase extension directions. So for example, this model 1, this is our base case. The angle between this extension direction and this extension direction is 45 degrees. Whereas if we go to model 4, where it's 22.5 degrees between extension directions, here you can see the arrows between the top row was the same as for all models. Whereas if we look at the bottom row, then we see that the extension direction second phase has changed. So again, we have these lines on the top surface of the models to help track deformation and to see reactivation on various faults. And hopefully what you can see is that the end of the first phase, the fault patterns are not exactly the same, but they're very similar. we're ending up with faults that are roughly perpendicular to the extension direction in all cases. We're seeing approximately a similar number of faults and approximately similar spacing of faults. However, you look at kind of the second row where you're looking at the end of the second phase, the fault patterns that are developing are quite different. So in the model with 45 degrees between the two extension directions, we can see a fault pattern which is fairly well defined as having two different directions approximately of faults that are exposed. We see some faults that have larger heaves on them than other faults. Then as we kind of head more to the right, where we have the model that has the smallest angle between extension directions, what you can see is the fault heave on the faults here appears to be significantly larger than it is on this model number 1. So to help kind of illustrate that, I'm now just going to show a line drawing of the 4 different second phase bits of the model. And this really helps to kind of take away some of the lighting issues with the photographs and really show the difference in the fault displacement on the first phase faults between model 1 and model 4. And again, you can see that the fault heave, which is the black area, is significantly larger in model 4. Also, as we looked at the marks on the top surface of the clay models and at the fault planes themselves, we could see that there is definitely an increase in dip slip motion on these first phase faults in model 4 compared to model 1. Again, the magnitude of extension is the same in all of these models. So what we're really seeing then on the top surface of the model is a difference between the component of normal versus strike slip on each models, or the amount of obliquity on each of these pre-existing faults. So as you decrease the angle between your first phase and second phase extension direction, you see an increase of likelihood of fault reactivation. We're seeing more faults that are being reactivated, but we're also seeing an increase of the dip slip component on the first phase faults. So now, if we look back and think about the second phase faults, those are fairly easy to pick out. You can compare the end of the first phase to the end of the second phase and kind of see which faults appear to be new. What you can see is there are new faults in all of the models, but it looks like the number of new faults is higher in the model with 45 degrees between the extension phases than it is in the model with 22.5 degrees between extension phases. So if we just base it on, okay, most of the normal faults formed during the first phase are approximately perpendicular to the first phase extension direction, we expect the faults striking roughly northeast southwest or first phase faults, and then other faults theoretically striking northwest southeast should be second phase faults. Again, I'm going to just pop to the line drawing, which I think really helps to highlight the difference in the number of new faults that are forming during the second phase extension. So if you just compare then model 1 to model 4, again, if you're looking for faults that are approximately perpendicular to the second phase extension direction, you can find a lot more faults with that orientation over here in model 1 than you do in model 4. And this is a function of a couple different things. So previously, again, I said that there was more dip slip reactivation in model 4 than model 1. And this partially helps to accommodate the deformation in the models, making it so it isn't as necessary to form new faults to accommodate that deformation. Also, this really highlights how the new normal faults form and how both their initiation and propagation is affected by the pre-existing faults. So over on the right here, we have a diagram of a fault growing through time during the second phase of extension. So starting at 1.7 meters of displacement during the second phase and then going to 2.4 centimeters during the second phase. And what you can see is the new normal fault initiates at the pre-existing fault and then propagates outward from the pre-existing fault. And this arrow here up in the right indicates the second phase extension direction. So you can see initially that new fault is propagating orthogonal to the existing fault here. But then as it propagates outward, it bends to be perpendicular to the applied extension direction. So there is a overprinting of the stress field near the first phase fault that influences this fault orientation. As you get farther away, though, you're ending up with a clay model feeling more of the regional applied extension direction. And so then what you see And the line drawings, we then kind of think about that model, is you have in model 1, you have a lot more faults that are propagating outward and bending, and initially perpendicular and then bending to reflect the regional extensional direction. Whereas in model 4, you have only a few faults that are actually initiating and propagating outward from those pre-existing faults. And some of this may be partially a function of the clay thickness and density that does affect some of the fault spacing. So depending on the clay cake that is used, you might end up with a different fault spacing and therefore end up with different fault orientations, but the general trend is still the same. And that the new faults will initiate and grow outward. But in general, where you were seeing more of a dip slip component on the reactivated faults, we're not seeing as many new faults. So after these faults initiate and propagate outward, they will inevitably run into other first phase faults. And in the models, there are two main types of fault interactions between the pre-existing faults and the new faults. The first interaction, which I have a green box around, is where the new faults terminate against the pre-existing faults. And this is revealed really only by watching back the photographs and making a movie out of it to see where the fault initiates and propagates, which direction it propagates to, and then where it ends. There are many cases in the models where it looks like, for example, here, that fault may cut across this larger pre-existing fault, but when you watch it, this is a new fault that propagated outward before the tip of this fault reached this area on the surface. The second type of fault interaction is then where new faults cut across an offset pre-existing faults, as indicated in the orange here. And interestingly, if you look at the percentage of total fault interactions and look at how many of the new fault interactions cut and offset pre-existing faults, I saw that the percentage of those new faults that can cut and offset pre-existing faults appears to increase as the angle of extensional phases increases. So it appears it's easier for the new faults to cut across the pre-existing faults with larger angles between the extension directions. So to summarize the series 1 models, I'd like you for a minute to just look at these line drawings and think about them not as pictures from a model, but as potential maps from the subsurface of something that you might see either in your data or in a presentation in another group. And I want you to think about what you would infer from these fault patterns just by looking at them. Because a lot of what this initial series highlighted is that some of the inferences we would make just based on fault heaves, fault patterns, just without any other information can be misleading. So what the models show is that the new normal faults will commonly initiate at pre-existing normal faults and propagate outward. And they do this initially perpendicular to pre-existing faults. So as you can see, there are cases in all of these models where I can find fault patterns that look almost perpendicular to each other. But we know that the extension directions varied significantly between the second phases of all these models. Also, the amount of dip slip versus strike slip on the reactivated faults in this is not proportional to the magnitude of extension. So if you were to look at these fault patterns without the other information, you may infer, oh, the faults over here in this map on the right, they must have undergone more extension. They must have been a larger magnitude of extension during the first phase on this map, which again is not true since they both underwent the exact same boundary conditions as far as the magnitude of extension. It's more of a function of how much dip slip versus strike slip occurred. So now I'm going to go on to the series 2 models. And in this case, instead of varying the angle between the extension directions, I varied the initial fabric development. And I did that by varying the magnitude of the first phase extension. So instead of worrying about the angle of E1 in this case, I actually just limited how much I would extend the model. And that is listed here in this table. So model A in this case didn't have any extension during the first phase. And then B through E then varied the amount of displacement up to model E, which is again our base case. And you can see that the fault patterns on the top surface of the clay model then are directly proportional to the magnitude of extension on these. And you have the most developed fault fabric then with model E and the least developed in model B. And after then documenting this and the differences between the initial fault fabric, I extended the model for the same magnitude in the second phase extension. So each of the models then underwent the same conditions during the second phase. And in this table here, I have the end of the first phase, again referenced, and then next to it I have the end of the second phase of the same area of the model showing the fault patterns. And what you can see is they look different. So model A didn't have any extension in the first phase, but models B through E did have a pre-existing fault fabric of varying magnitudes. And what these models show is that the degree of development of the first phase fault population influenced the fault geometries that developed during the second phase extension. So this poorly developed first phase, which is model B, resulted in a series of long parallel normal faults that formed during the second phase extension. The moderately developed first phase, which is C and is well seen a bit in model D, this is where many of the new normal faults link with the reactivated first phase faults, and they form composite faults with zigzag geometries. Whereas the model E, which is again our base case model, this had the well-developed first phase, and most of these new normal faults intersect the reactivated first phase faults, either by cutting across them or by terminating against them. So those fault interactions that I was talking about previously. Now, the really interesting thing about this model series is not just looking at the end of the first phase and comparing it to the end of the second phase, but it's also about how these fault patterns developed during the second phase. And so I looked at 5 different intervals then during the second phase to really compare what the fault patterns looked like, how the faults were growing and interacting over that time. And one of the main conclusions was that the dominance of the first phase fault fabric relative to the second phase really depends on the magnitude of extension during both phases of deformation. This in itself is not really a very unique conclusion, but as you start to look at the different fault patterns at different time increments, it becomes very powerful because you start to see how fault patterns at a certain amount of displacement in one model look very similar to fault patterns for a different amount of displacement in another model. So for example, if you kind of compare models D and E, you start to see that the end state of model D looks not entirely dissimilar from some of the earlier states of model E, and you can do that throughout the models. And so I quantified the magnitude of displacement on this first phase and second phase fault. I'm sorry, not the magnitude of displacement. I quantified the length of the faults during the second phase of displacement on all the faults, just to see what faults were gaining length when. And so in this series of graphs here, you can see at the end of the first phase, most of the faults have lengths that are perpendicular to the first phase extension direction, indicated by the black bars. But by the time you get to the end of the second phase, we see that the sum of lengths perpendicular to the second phase, which is this darker gray, has increased significantly. However, in the middle, you end up with a significant amount of fault segments that are oblique to both extension directions. So especially if you are observing the middle phase of a model, it can be very difficult to parse out what is the dominant extensional phase, what is the magnitude of various extension directions, because the fault patterns are still developing. Oliver Duffy, who's now at the BEG, took this to and took the analysis of these fault patterns and applied some topological analysis to it. And so this is just, I wanted to briefly highlight, in his paper from 2017, he went through and actually looked at model B and model D, and then also look at the different development of the first phase to kind of quantify how the different fault pieces are connected, and looking at the branching relationships and the different ends of the faults. I would definitely recommend you go read that paper for more information on that, because I kind of understand it, but not completely. My goal was really to more document the more qualitative pieces that you could see from these fault patterns. And so I was very glad that he could then take this and take it into a little more of a quantitative realm. So one of the things that I really noticed when working on this series of faults was how the faults linked together and formed the zigzag fault geometry that I talked about for model C. And so I just want to take a moment to look at that. So in series 2, and especially in model C, we see some linkage of first phase and second phase faults that are creating these composite faults that have a zigzag geometry to them. And by zigzag, I mean that there are oblique slip segments associated with the first phase faults, which again are roughly perpendicular first phase extension direction. And then there's other components of this composite fault plane that have normal slip segments, and these are associated with the new second phase faults here. And so on the, again, this is a photo of the top surface of the model. You can see that the lighting direction is now from the right, and these faults are actually all in shadow, but you can hopefully see how they're formed a hard-linked fault surface here using some pieces of the first phase faults and then with second phase faults linking them. And then on the right, I have a line drawing that just highlights this linkage through time. So this starts with the end of the first phase extension, and then we have 1.2 centimeters into the second phase, increasing up to 3.2 centimeters in second phase. And you can, using the photographs, you can watch how the faults and new faults initiate and propagate outward, and then link with other first phase fault segments, and then ultimately form a through-going fault. So related to that sort of fault interaction where they've linked together and formed other fault segments, I just want to then go back to talk about fault interactions again. And hopefully most of this diagram, this slide looks familiar. So the two main type of fault interactions other than the zigzag faults where they form together, again, are where the new faults terminate against pre-existing faults and new faults cut across and offset pre-existing faults. So in these series of models, what I thought was very interesting was that the proportion of the new faults terminating versus new faults cutting. And what you can see is that, as you increase the first phase extension, you end up with a total number of interactions increasing throughout, which makes sense. There's more faults that you've created during the first phase, there's more of a chance for a fault interaction. But the other interesting piece is that if you look at the relative percentage of the interactions and which kind of interaction dominates. So for example, if we're looking at model B, 100% of the fault interactions that we see at the top surface of the model at the end of the second phase are new faults that cut across and offset the pre-existing faults. Whereas if we look at model E, which is our base case model again, we're seeing that only 60% of the new faults are cutting and offsetting the pre-existing faults. So we can see that the relative importance then of cross-cutting interactions actually decreases as the development of the first phase fault population increases. And this would also then be true if you were to look at the fault interactions through time of each of the models. And so then the relative percentage of faults that are cutting versus the terminating could be partially determined by the magnitude of extension during the second phase. And so to wrap up the series of models, I have this diagram here over on the left, which highlights both the magnitudes of displacement that happen for each of the models. It has a line drawing of part of the model surface. And it also has then a rows diagram just to point out the dominant fault populations in each of these line drawings. And this kind of hints to that this paper, while I've glossed over some of the quantitative pieces, that there was a fair amount of work gone in to try to quantify what exactly was happening with the fault populations, not only the number of faults, but then also the length of faults, and to understand really what the differences were between, for example, this parallel fault geometry, the zigzag fault geometry, and the intersecting fault geometry. Because by looking just at the top surface of the clay models, it's easy to say that, okay, model C looks different than model E, but it's much more useful to have a quantitative measure of the characteristics of the fault populations. So to then summarize that, the fault patterns in the models belong to one of three categories. So the reactivated first phase faults are dominant in parallel. That is not correct. That's an awesome typo on my part. I apologize. Where the new faults are dominant is where the parallel fault geometries dominate. Where neither first phase faults nor second phase faults are dominant results in the zigzag fault geometry. And then where the first phase faults are also dominant results in your intersecting fault geometry. And the dominance of first phase faults relative to second phase faults, again, depends on the magnitude of extension in both phases of deformation. So this is the paper then that came out in 2011. And we had a preserved layered model that we had a lot of work we had worked on looking at different fault orientations, different fault patterns with depth, but we didn't have a lot of really good documented natural examples to compare it to. And approximately between 2011 and 2015, there were a number of great field studies that came out and were published about various basins throughout the world that really helped to inspire us to do some more analysis. So this is one example of a paper that was just very useful, both for thinking about different ways to analyze some new models, and then also for our natural analogs. And this is Casey Nixon's 2014 paper that was in AAPG Bulletin. And he was looking at the fault interactions and reactivations in Milne Point, Alaska. And what you can see here are we have maps on a shallower horizon. So that is this column to the left, and then a deeper horizon on the right. And the top maps are two-way time. And then the bottom maps are just highlighting the two different fault trends. And in this area, there are two generations of faults. There's Cenozoic north-northeast trending faults, and there's Jurassic west-northwest trending faults. And these highly compartmentalize the upper Triassic to lower Cretaceous reservoirs. And Casey did a fantastic job of documenting changes of the fault trends, fault interactions with depth, including fault throws in areas of complex fault interactions. And this really gave us a lot of material to compare to the models and think about different analysis we could do to then look at and compare with these natural examples. So the layered model that I refer to that we used is then this model that you see here. And this model, again, has the same boundary conditions as our base case model with two phases of extension. But instead of just building a single clay cake, we built a model with tinted layers of clay. So we had a white layer, a red layer, and a gray layer. They have the same mechanical properties. It's just adding just enough color to be able to tell them apart after the model has dried. And so we built this model and infilled after the first phase extension and second phase of extension, and then allowed the model to dry to preserve it. And unlike sand models, which you only have to wait a day, for clay models, you have to let them dry very slowly. And so we waited approximately 6 to 8 weeks for this to dry out. But once we did that, we could then make very thin serial sections through the model. And we created 21 serial sections that were 1 millimeter apart, where we had a work study student who sanded a millimeter off, took a photo, sanded a millimeter off, took a photo, and did that to create the 21 serial sections. He was very patient. And these photos were then imported into Petrel to make horizon maps, and also looked at just in the cross section to look at the fault geometries and make some comparisons in the three intervals that you see here. So at the 0, 10 meter, and 20 millimeter intervals. So this was in my infancy of Petrel usage. So I would probably make a little bit better maps today. But what you can see is that if we're looking at then a few different horizons in the model, so this horizon 1 was the layer added after the top of the layer added after the first phase extension. Then we have horizons 2, 3, and 4, which match up with 2, 3, and 4. And then we have a picture of the bottom surface of the model, which again is a photo that we took after the model hit dry. And you can see here that I've just annotated, you have the extent of the rubber sheet and the overlying silicone polymer, which is shown on the photos. And that pretty much is roughly between the two faults that you see in the photographs. Occasionally, you have a fault, a single fault that may extend a little farther out from where the edge of the tape was that was attaching the rubber sheets. But in general, you have the deformation focused right under where the silicone polymer was located. And so after pulling this into Petrel and then making some maps, we could start to then look at the different fault patterns at these different horizon depths, and also start to correlate faults then both laterally and with depth. And this is work that Martha Withjack did the bulk of because I was working full-time. And while this is definitely something that we wanted to advance and to really look into, it's just I didn't have the full capacity to really dive into this as much as needed. So I am eternally grateful for her bringing this forward and bring it so it could see the light of day. What you can see is that now we've color-coded the faults so that the blue faults, again, are perpendicular to the first phase of extension. Now, in this case, the diagrams have rotated. So instead of your arrow then pointing up and to the left for E1, since we're looking at a small slice of the model, we've rotated it just for the ease of the eye in comparing the different sections. But it's the exact same conditions as the base case model. And so what you can see if we compare just the different horizons throughout the model is that the blue faults, which are the first phase faults, are much more common at depth, whereas the second phase faults are more common at the shallower levels. You can see the strike of the first phase faults is fairly consistent with depth. It's generally perpendicular to the first phase extension direction, again, as we observed on the top surface of the base model. And then we also see that the strike of the second phase faults varies with depth. And again, this H1 was based on photographs. So this is, we could actually watch these faults growing during the model run. So we know for sure that these are faults that were formed during the second phase. You can also see that the style of faulting then likely varies with depth, just based on the orientation of the faults and based on what we saw from observing the top surface of the clay model. So the normal faults that occur at the shallow levels, second phase faults are common. Those probably are purely a dip slip. Whereas at depth and near the bottom, we likely have oblique slip faulting occurring where the first phase faults are more common, since we previously observed that those are more likely to reactivate with both normal and strike slip components. What we also see is that many of the faults are actually hybrid faults. They're composed of second phase fault segments that emanate from the tip of deep reactive first phase faults. So for example, you have fault 2 and 2A, where 2A is propagated outward. There's 3 and 3A, where 3 propagates outward. 4 and 4A, we see it throughout the vertical section of the model, which again matches what we saw from observing the top surface. In addition, there are 2 broad categories of fault interactions that we see in cross-section. And this is again building on the previous thought there was, okay, a couple of fault interactions that we saw on the top surface of the model. But again, this is quantifying a little more and looking not just at if the faults are intersecting or terminating, but this is also taking into consideration whether the faults are synthetic to each other or if they're antithetic. So in the case of synthetic faults, there is upward propagation from the fault tip. So that would be the faults that I was just pointing out, like fault 2 and 2A, 3 and 3A. Also, we're seeing upward and outward propagation from the fault surface, and you're likely to see fault linkage. Whereas if we look at antithetic faults, so for example, if we're looking at fault 7 and how it cuts through 4A and 3A, if we look at some of faults over here that are coming and cutting over to fault 4, we can see there the antithetic faults are much more likely to cut and offset the pre-existing faults, and some of them do also terminate against the pre-existing faults. So we're also being able to document some of these differences in the model, both on the top surface of the model and with depth. There's a significant number of fault interactions that are actually present once you start looking at these models. And in the sake of time, I'm just going to go through one of them. And I would encourage you, if you'd like to learn more, then please look up the 2017 paper, because there are multiple instances that have been documented in this sort of fashion here. So this example is one of the synthetic fault interactions. And it is this fault 3 and fault 3A that I was just pointing at. And so here at the top, you see we have it in cross section. So we have it at serial section starting at 0, and then with serial section at 10 millimeters. And then at the bottom left here, we have the map view on 3 of the horizons. So again, the 0 millimeter would be this section, and then 10 millimeter would be this section. And then in the middle here, we have a diagram that's showing the fault separation along this F3A fault. And this fault is very interesting because not only can we see in the cross sections, but also on this diagram of fault separation, it's very clear that the highest displacement along the fault is actually next to this fault F3. So the contours here are magnitude of separation along the fault plane. And instead of having a nice bullseye fault displaced in the middle, we can see the highest displacements right where it branches from fault F3. So from this, we assume that this is the nucleation point, and then the fault propagated outward from this location. And so it propagated both upward, and then it's starting just below the 10, or just before the 10 millimeters, and then propagated towards 0 millimeters and 20 millimeters. And then what you can also see on this is the branch line then between this fault F3A, which is this, and then fault F3 that it branches from. This branch line actually plunges at about a 50 to 60 degree angle. So it isn't a horizontal branch line. It also has a bit of rugosity to it. So it isn't a simple branch line there. So this also really highlights some of the complexity that you see that we were able to then compare to, especially some of the work done by Casey Nixon, but then also on the Taranaki paper by Giba, to help show that we can observe the same things in the models as we're seeing in nature. So that was very useful to have those natural examples. And lest you think that that was the end of it, and that we have no other work going on at Rutgers. So now this is my very brief plug for the Rutgers Modeling Lab. So there is also additional regional work that's been done at Rutgers based on some of the more recent published natural examples, and then also as this work has evolved just from things that I've discovered. So some of the other physical modeling work that was done or has been done since 2012 on the non-coaxial multi-phase deformation front. And a lot of it isn't the two phases of extension. There's extension followed by shortening, shortening followed by extension. We have strike slip followed by extension, and then also extension followed by strike slip. And I borrowed a diagram from a master's thesis from 2013, just to kind of highlight some of the variability and the various setups that have been going on. And so this should look very similar. This is the same as my setup, just rotated, and it highlights just the displacement directions and then the extension direction you get from that. And then on this bottom, it shows the variation in extension directions that are possible with the Rutgers modeling apparatus. So at least from what I've seen, Rutgers is fairly unique in that they can model different directions of deformation in multiple phases with a fair amount of ease. So one nice example then of this deformation that was documented by Christian Putra was strike slip followed by extensional models. And in this case, he varied the amount of the first phase displacement, which then varied the magnitude of the first phase fault population. So very similar to my series 2 models. And what you can see then is that, so the first phase was the strike slip deformation. Second phase was then just pure dip slip deformation. And you can see that the fault patterns, again, that develop if you're comparing, for example, the model 0, which doesn't have any strike slip deformation, versus the model 5, which has the same magnitude of displacement for both phases, is you're getting fault populations that are very different throughout the model. And you're seeing an increasing obliquity of the second phase faults. So this is just another nicely documented example of how, in this case, pre-existing strike slip faults can then affect the newly forming deformation patterns. And so with that, I am happy to take questions.
Thank you, Alissa. We've got a few questions on the board. First is from Mark Adaminsky. How do you emplace the clay so that it does not have pre-existing weakness zones that would influence subsequent faulting?
Very carefully. So when you put in the clay out, you kind of scoop it in and you smooth it out. And you generally also let it settle for a bit so that hopefully some of the air bubbles are settling out and you're kind of making sure that's evenly distributed. Theoretically, in the process of smoothing, you are forcing the clay particles to align a little bit in one direction as you're pushing them down since clay particles are elongated. But in general, I think we've shown, or multiple studies have shown, that you're not really imparting any significant pre-existing discontinuities just in the clay cake. You would definitely need to add like some other factor in there to have that.
Mohammed Gandhi had a question about examples from the real world. I guess you gave a couple. Are there any other examples of these polyphase extensional systems that one might look to in the literature?
Oh, there's a bunch of them. If you're looking for, I guess it depends on what you're looking at, because it feels like since I did my modeling studies, there was a lot of other examples that came out and were documented. I think it's Keep and McClay. So in the 90s, Ken McClay with some of the students did some multi-phase modeling studies, and Lorenzo Bonini did one as well. But then I think as either 3D seismic has gotten better and other areas have been explored, there's been a lot of good examples of national instances of multi-phase deformation. So the Taranaki Basin in New Zealand is a great one, especially because the rules for seismic are a bit different there and things are released more readily. The Jeanne d'Arc Basin is a good one just because that's been documented and explored for a while. Of course, the North Sea has a bunch of stuff, and we have a lot of good examples from there as well.
See a question from James Kessler. Do you think these processes or mechanisms would scale down to natural fracture development and help us predict patterns of natural fractures where we lack empirical data?
So one of the things that really struck me about this once I started working on conventionals and thinking about this is if you think about, okay, I know on a seismic line, there's going to be a scale of observation by which I can't get past. And then there's going to be, and then you look at the core and you're like, oh, wow, okay, we can kind of see that some of this is fractal and we're seeing like larger patterns and smaller patterns in the same area. And I think that's really true for the physical models. And this is where I think that because it's with the clay model and you can watch more detailed fault interactions and especially see how the faults grow, it kind of gives you a feeling for how exactly faults may have propagated and linked with each other, which would then highlight where there could be more deformation and more fractures. I didn't show it, but I believe it's the 2011 paper. I made some thin sections of the models, actually. It might also be, I think it's also in the 2017 paper, where I highlighted that a lot of the fault interactions I saw on the surface of the models, the photos, were being replicated at the microscale in the models. So I think a lot of these processes are definitely scale independent. And so you can then take those ideas and project them to where you would then expect fractures, especially when you're looking at reoriented stress fields around the different faults.
A new question from Antonio Rabaglia. Is the wet clay affected by strain rate or just the silicone?
It is partially affected by strain rate. I'm sure if I ran it real fast or really, so a couple orders of magnitude faster or slower, it would be affected. Actually, one of the bigger issues earlier on when I was working on my dissertation was the density of the clay. And it turned out that just over time, the density of the clay that we had preferred to use, it kind of creeped a little bit. So it was less dense, there was more water in it. And that actually had an effect on the spacing of the normal faults and the amount of ductile versus brittle deformation. So it's something that it's good and bad, because in the clay models, it means that you have a little more flexibility for what you're trying to model, but it also means then you do need to be cognizant of the material properties and material of what you're using.
Question from Alan Irving. Let's see, while he's looking up the 2017 paper, is there any quantitative measure of dissimilarity between the models after the first deformation phase?
So I guess it depends on which series of models. In the series 2, where I varied the initial fabric, I did some work quantifying the different properties of the fault populations. So the orientation of fault segments that were there, the lengths, and don't remember if I did density or not, but trying to really quantify what I thought that the fault populations were present. When it came to the first series, I did not do any quantification of the differences between the first phase, other than to look and see that they looked generally to be similar, just because anytime you run even any model of clay or sand, you're going to get some variability in where the faults appear in length and displacement.
Well, we don't have any other questions open. I'll give folks a minute or two to. I guess I did have a question about your second model, the one. Were there any issues with deformation as that desiccated? Did you get additional?
Yes.
Like isotropic, it should be shortening isotropically, right? In horizontal plane. So
yes.
Were there any issues with that in the model?
So part of the process of drying the model is to put plastic over it and try to encase it so it dries incredibly slowly. The idea being so that it has enough time to just kind of evenly shrink throughout, and you're not really concentrating any of the shrinking or potentially cracking of the model. And also we put a few different cuts in, so kind of giving it planes along which to shrink, so that you all kind of get like a section like yay big that is all intact, and then you cut it so you have a piece you can look at later, but you've also given it places along which to contract naturally. There were unfortunate cases documented in my time. I don't think any of mine did, but I could be remembering that incorrectly, that would then potentially crack in other directions, which was very sad. And you also hopefully didn't get it kind of bending up or, bowing up. And again, that was really you turn on all the humidifiers and hope for the best. Oh, I see that Ian's here. I should say that, so Ian Sinclair at Husky Energy, this is all partially his fault. He's the one that started the initial study to look at different fault patterns and what could potentially make orthogonal fault patterns in the Jabbar Basin. So it is, for better or worse, he is partially responsible for kind of providing the impetus for this work.
Well, it looks like we have no further questions, Alissa. Thank you very much for your presentation today. And for all of you still online, we'll have a recording of this for you to interrogate at your leisure in about a week or so. All right, thank you, and we'll see you at the next PSGD webinar in January.
Thank you, everybody.